All right, in the last video, it was cut off. By the way, I'm using this free version of this program to do these videos. So I can only do like 15 minutes at a time. That's why I got to break them up, just to let you know. All right, so we've moved the decimal place, one place to the left past the 6. So there's a total of 11 places. So we've taken care of 1 by moving it past the 6. So I need 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then of course you have the 6. All right, and of course there's a 6, 7 after that. All right, so this is a good example of why we use scientific notation, right? It would be pretty much a pain to write this number every single time, and this number actually turns out to be a very important number in the physical sciences. It is called, just to let you know, not that we're going to encounter this right now, but this 6.67 times 10 to the minus 11th is the strength of what's called the universal gravitational constant. All right, so that's why we use that one all the time. All right, let me do, let's see, so part C, there's some equations here, or some calculations. Here's part C. So the first one is 2 times 10, let's see, what is it? It's, let's see, did I write that down right? 2 times 10 to the third, that almost looks like a minus, sorry about that. Here, let me try to erase that. So it's 2 times 10 to the third plus 1 times 10 to the minus 2. Okay, so it's, and I think it says to do this in like normal units. All right, so here, let's just write everything. So 2 times 10 to the third would be 2,000, right? And then 10 to the minus 2 is just 1 times 10 to the minus 2. So that would be plus, right? Because we got the plus sign right here, plus 0.01, right? That's what 10 to the minus 2 is, 0.01. So this is really simple. It's just 2,000.01. That's it. All right, and the next one now, you need a calculator to do this one. So this is 1.99 times 10 to the 30th divided by 5.98 times 10 to the 24th. Okay, so to do this, you make sure you know how to use your scientific calculator. For example, just to let you know, if you have a Texas Instrument, make sure for the times 10 part, so anytime you're doing times 10, you never hit times, you never hit 10, right? For a Texas Instrument, that function is, there's an EE button that you have to hit. Okay, for Casio, let me think, what is it for Casio? It is an EXP button. So instead of times 10, you hit the EXP button. All right, so keep that in mind when you're doing these. All right, so this is done correctly. So 1.99 times 10 to the 30th divided by 5.98 times 10 to the 24th comes out to be, so let's see, it is 332,775.9. So 0.9. Let's see, 0.9. So I'm going to write this. I'm going to rewrite this in scientific notation. So notice I only have 3 significant figures in the numerator and in the denominator. So I really only need 3 significant figures when I do this. So let's see. It's going to be 3.3, and so since the 2 is followed by a 7, I've got to round that up. all right? So 3.33, and then, so the decimal place was right here, so I had to move it 1, 2, 3, 4, 5, right? So it's going to be 3.33 times 10 to the 5th. All right, so practice that, okay? Practice that with your calculator. The next one is just multiplying, okay? So it is 3.16 times 10 to the 7th times the quantity 2.99 times 10 to the 5th. And that comes out to be, let's see, did I actually, yeah, I did calculate it. It turns out to be 9. I'm just going to go with 3 significant figures because this one only had 3 significant figures. All right, so it's going to be 9.47 times 10 to the 12th. All right, so practice that. Again, you never hit times, you never hit 10. For a Texas Instrument, you got to know your calculator. Texas Instrument, you use the EE button. For a Casio, you use the EXP button. If you have a different type of calculator, I'd have to look at it to be able to figure that out. All right, let's move on to, what was that? That was part C. So now question 3. All right, for question 3, they ask us, it's very easy, much easier to do if you look at the figure on page 14 of our e-text. It's also a figure that's in the review as well. Okay, so I'm looking at this figure. It basically has the Earth orbiting the Sun, and then all the different constellations of the zodiac. Okay. All right. Let me scroll back down to the question. Sorry, I was looking at the figure. All right, so here it is, number 3. It says, the vernal equinox is now just entering the constellation Aquarius. By the way, that's not true. It's still in Pisces, okay, so it's just to let you know, right? It's still in the constellation Pisces, but in about 600 years or so, it'll actually technically move into the constellation Aquarius. Anyhow, so they're saying that we're going to assume that it's already part of Aquarius. All right, and then it says, in what constellation will it lie in the year 10,000 AD? Okay, so in 10,000 years, where will we find the vernal equinox? Okay, so it's right now it's in Pisces, but they're assuming that it's already in Aquarius. All right, so we'll make that same assumption. That's not that big of a deal. So just to remind you, the reason that the vernal equinox moves, of course, let me back up just a little bit. 2,000 years ago, during the time of the Greeks, the vernal equinox actually occurred in Aries, right? That's actually, we still talk about the first point in Aries as the 0, 0,0 for the right ascension and declination. Anyhow, because the vernal equinox used to be in Aries back during the time of the Greeks, but now in modern times it's in the constellation Pisces, and it's moving because of this wobbling that the Earth takes, that takes 26,000 years to wobble around once. So in 26,000 years it wobbles all the way around all 12 constellations of the zodiac. Okay, so what we do is it's actually really simple. You just take you have 12 constellations of the zodiac, so we know that it takes 26,000 years divided by 12 constellations of the zodiac. They're more or less the same size in the sky. They're not exactly, but we'll make the assumption. So that basically tells us that so when you divide this, it tells us that every 2,167 years, roughly, once every 2,167 years, the vernal equinox will go from one constellation to the other, right? So it started in Aries. It's now in the current time in the constellation Pisces. All right. So anyhow, if that's true, all right, if because of precession, the vernal equinox will keep moving, we just say, all right, well, in 10,000 years, so how many times will it move, right? So you just take 10,000 and you can divide it by roughly 2,167, and you get. What do we see? If we took in 26,000 years, it would go all the way around and return back to where it currently is in the constellation Pisces. But if we assume that it starts in Aries, if it's not exactly true. This 10,000 divided by 10,000 years in the future, divided by in steps of 2,167. It turns out to be about 4.6, right? Roughly 4.6. So it'll have moved 4.6, so 4.5 constellations. Okay, so if we assume that it's in Aquarius, then we basically take 4 steps, right? So it'll be in Capricorn, then Sagittarius, then Scorpio, right? So we've taken 3 steps, and then the fourth step puts us in Libra. Okay, so 10,000 years from now, the vernal equinox will occur in Libra, right? 10,000. 12,167 years from now, it'll occur. It'll be in. I forget what the next. What's the constellation right before Libra? I usually remember these things. I think it's. What is it? Virgo. Yeah, it's Virgo. Yeah, I don't know why I remember. All right, and then after that it's Leo, and then Cancer, Gemini, Taurus, and you're back to Aries. Okay. All right. So anyhow, that's number 3. All right. Let me read number 4. So number 4 says, relative to the stars, through how many degrees, arc minutes, or arc seconds? I'm actually going to say and arc seconds. Does the moon move? A, in 1 hour. B, in 1 minute, and C, in 1 second. Okay, so we will work on these. Okay, so for A, it's 1 hour. All right, so 1 hour. That's supposed to be an H. All right, so here's the thing. We got to know these conversions. This is really important. We know that the sky of there are 360 degrees in a circle, right? That's just defined. There are 360 degrees. All right. It turns out that when you get down to 1 degree or less, it's convenient to break up 1 degree into 60 equal parts. And one of those parts is called an arc minute. So there are 60 arc minutes. Oh, and by the way, you can write degrees with this little circle here, or you can just write 1 DEG, right? That's perfectly fine. So 1 degree is the equivalent of 60 arc minutes. All right. And then 1 arc minute, so when you get down to one of those, so you got a degree, if this is 1 degree, and you can't really draw this very well. So you break this up into 60 equal chunks, and so that 1/60th of a degree is an arc minute. So then you can further break that arc minute into smaller little chunks, and so 1 arc minute is broken into 60 arc seconds. All right, so just to let you know, for astronomy uses this all the time. 1 arc minute is about the limit of the human eye by itself, sometimes called naked eye observations. All right. Now, in this problem, all right, I'm just going to tell you right now, they're